Hi and welcome to this second video on variable acceleration, and what we're going to be doing in this one is looking at how we can use calculus to solve problems involving variable acceleration. So we saw last time we can describe motion in terms of displacement as a function of time, and if we can do that we can link it to velocity and acceleration as well. So here we go. So last time, if you looked at the previous video, we had a displacement time graph and we were working about how far away from the origin our particle got, and we found that by finding displacement using a turning point, which is the maximum. And so we realised that if we've got a function in terms of displacement, then ds dt, our turning point on that was when that thing was equal to 0. Well, ds being the change in displacement, dt being change in time, and clearly the change in displacement, change in time, that is velocity. So basically what we're saying is that if we've got a function that is displacement in terms of time, if we differentiate it, we get a function that describes velocity. And in our previous example, we had maximum displacement occurring when ds dt was 0, that's when the velocity was 0. And then if we had an expression for velocity, and I went for, okay, let's go for this one. So if we differentiate velocity, differentiate v, we get dv dt. Same idea, change in velocity over change in time. You can probably see where this is going. Change in velocity over change in time is acceleration. So the three things, displacement, velocity, acceleration, are all linked together via differentiation. Get from one to the other. And we do that by, if we start off with displacement, differentiate, we get velocity, differentiate again, we get acceleration. And I see these things very much as almost like a ladder. Displacement at the top rung, velocity in the middle rung, and acceleration at the bottom. And obviously we've only got half of it there, the differentiation bit. On the other side, we say, well, if we're at the bottom rung, if we've got acceleration, clearly we're going to integrate to get to velocity, integrate again to get displacement. And this graphic here is one that I always have in my head when I'm working with displacement, velocity, acceleration. Am I going up a rung, down a rung? Am I differentiating? Am I integrating? So the final thing to mention is, particularly on the integration side, is that when we're integrating, if you're doing an indefinite integral, you get a constant term. That constant term still exists, we can't forget about it, and often in these situations it represents an initial displacement or an initial velocity. And we'll see that as we go through the next examples. So here we go, we've got a particle moving in a straight line. At time t seconds we've got displacement, which is given by that equation, t to the 4 minus 30 to t plus 12. And the first question says find the velocity of p when t equals 3. So here we go. Velocity is ds dt, so my first job is to do some differentiating. So I'm going to differentiate my expression here. So that gives me 4t cubed minus 32. And then, so this thing is velocity, and if I want a velocity when t equals 3, all I'm going to do is plug 3 into there, and that tells me that this thing is moving. It's going at a hell of a speed. It's going at 76 meters per second. Right. So that was a straightforward, can I get from displacement to velocity, and then use my velocity expression by subbing in a value. The value at which p is instantaneously at rest, so the value at which velocity is 0. So we're going to plonk that in there, so just put that equal to 0, and then do some solving. T cubed equals 8, so it's instantaneously at 0 when t equals 2. Okay, all fairly straightforward so far. And then part C, let's find the acceleration. So acceleration, if I know velocity is where it's gone, this one here. Velocity is 4t cubed minus 32. I'm going to differentiate that, so differentiate it again. Acceleration being dv dt, or if you prefer the second differential of displacement, d squared s over dt squared. Either way, differentiate it again, so I'm differentiating this. I'm going to get 12t squared. And when t is 1.5, plug that value in. And there we go, it's accelerating at 27 meters per second squared. I've got to be honest, looking at, I do find this topic kind of the differentiation and, as you'll see in a second, integration are all reasonably straightforward. And it's just a case of then just popping in values and away you go. So hopefully you'll find that this particular section is not too challenging. On we go, second example. So we've got a particle moving in a straight line. We're given some information. So when t equals 0, appears at point A, and it's moving with velocity 8 meters per second, and we've got an expression for acceleration this time in terms of 2 minus 2t meters per second squared. So here we go, find an expression for displacement. So I'm going to go the other way this time. I'm currently on the bottom rung of my ladder, and I'm going to go up my ladder, so we're going to do it by integrating. So velocity is the integral of acceleration. So do the integrating. There we go. There's the plus c. So now we've got to look back and have a look at the information we've got about velocity in the question, which is there. Okay, when t equals 0, velocity is 8. So we're going to put that in here. So when t equals 0, v equals 8, plug it all in, and what do you know? We've got a value of c, which is 8. So therefore my expression for the velocity is that one there, v equals 8 plus 2t minus t squared. The question is asking for displacement. So I've got to go up another rung of my ladder, so I'm going to have to integrate velocity. That's going to give me displacement. So again, let's do the integrating. 8t plus t squared minus t cubed over 3, and again there's the plus c. So now I'm going back again and saying, right, well, if I've got a plus c, what information have I got to be able to figure out what's going on? And we know that when t equals 0, p is at point A, and it's moving from A to B, so that means displacement is 0 as well. Plug all of that in, and fairly obviously we've got a value of c at 0. So there is my expression for displacement in terms of t. Right. On we go. Right, next part of the question says show that P does not reach B. We're told that AB is 30 metres, so essentially what we've got to prove is that P doesn't, or the displacement never gets to 30, so how are we going to go about doing that? Well, our maximum displacement from A occurs when ds dt equals 0, i.e. at the point at which this object is accelerating along a straight line, and it kind of comes to a stop instantaneously, it's at rest, and it turns around and comes back the other way. And that point where it's instantaneously at rest is when velocity is 0, ds dt equals 0. So we've got ds dt, which is that one, or velocity, which is the same thing, that thing there. So we've got to put that equal to 0, do some factorising, and we end up with t equals 4. Clearly from this one here, we're going to get t equals minus 2. But in this particular context, time, we can't have time as a negative, so we can ignore that one completely. So we know that the maximum displacement occurs when t equals 4. So the next thing we're going to do is say, well, right, what is that displacement when t equals 4? So let's go back there. There's my displacement expression from the previous slide. Well, there it is up there. Plug in 4, and we end up with the maximum displacement is 26 and 2/3. So final thing I've got to do is actually physically answer the question. So I need an extra statement to go in here because I've come up with a value, but as ever, I can't leave the examiner to draw his own conclusions from what I've found. I need a statement to say that, okay, clearly, since 26 and 2/3 is not 30 metres, P never gets to point B. Right, that's that bit sorted. And then on we go for the last bit. It says the time it takes for P to return to A. So the point at which it returns to A, that's when the displacement will be 0. So I've just got to stick a 0 into my displacement equation, which is, there we go. So we've got 0 equals 8t plus t squared minus t cubed over 3. Now I've got to do some solving. So again, how you choose to do it, up to you. You calculate can handle a cubic. I'm old school. I'm still going to factorise it. And from there, we're going to get our value of t equals 0 from that part. And that's the one that says, well, we knew we were going to get that solution because we had it up here at the start of this motion. When t equals 0, the particle was at point A. So we already knew that bit. What I need is the solution coming out of here. And again, it's up to you. Do you go quadratic formula, or you just kind of take the easy option and chuck it into your calculator? Either way, you're going to get a value of t equals 6.63. And there we go. So that's the time it takes for t to return to A. Sorted. And final bit we've got to do here is just a more general example. So what we've got is particle P starts from the origin, moves with acceleration that's A, and initial speed that is U. Okay, so that's all we're given. So we've got to find the expression for the velocity. Okay, so if we're going to find the velocity, we know the acceleration is A. So in order to get to the velocity from there, we've got to integrate. So A is just a number in this case. It's a constant value. And so if we get velocity, which is the integral of acceleration, if I integrate it, I get that. And now I've got to think, okay, I've got this constant integration. What have I got in the question that tells me about what's happening with the velocity at any point? And there it is. We've got an initial speed that's u. So what we're saying is when t equals 0, v equals u, and we've got that, so we end up with that, and we end up with v equals u plus at. Okay, and at this point you might be thinking, oh, there you go, I recognise that. And this is where I personally think math is just fantastic, when all these kind of things start linking together. And you can possibly guess where I'm going with the next part, with part B, the displacement of P. Thinking, okay, which one of the CVAT equations is going to pop out of here? Well, let's just have a look what happens. S is the integral of V. So I'm going to integrate V, so that's a constant, so that becomes ut. There's t squared over 2. Oh, that's starting to look familiar. And what do we know about our C? Well, when t equals 0, the displacement starts from the origin, so that means S equals 0. So we've got that. So C equals 0. And so therefore what we end up with is S equals ut plus half at squared. These look familiar. Of course they do. Isn't maths viril?